Before we touch any wastewater words, I want you to notice something. When you cook, you don't just follow a recipe. You think, what is happening in the pan? What is it costing me? Is it safe? Will it turn out okay? That is not school thinking. That is real life thinking. And today, I'm going to show you the most important thing an operator learns. You don't just learn terms, you learn how to think in a chain reaction. Because in this job, nothing is just one number. Every number is a story, and every story has consequences somewhere downstream. So here's the promise. From today onward, whenever you hear a wastewater term, BOD, ammonia, pH, flow, you will not just memorize it, you will run it through a loop. This loop is how professionals stay calm, how plants stay stable, and how rivers stay alive. Okay, picture the plant like a living city. It has streets and gates. It has workers. It has rules. It has a rhythm. And most days, the rhythm is predictable. But today, it's Monday. Rain is falling, the streets are shiny, the storm drains are awake, and somewhere upstream, an industrial building opens a valve. Maybe they cleaned a tank. Maybe they dumped a washdown. Maybe it was an oops. But here's what matters. A stronger than normal slug hits the sewer. Not a little change, a sudden punch. The wastewater comes in thicker, darker, heavier. And the lab tech at your wastewater plant looks up and says, "Influent looks strong today." You hear one phrase from the control room, high BOD. Now I'll ask you something, and wrong answers are welcome. What do you think happens next? Does the plant remove it all? Do the bacteria just feast on more BOD automatically? Hold those thoughts, because now we're going to run this event through the operator's loop. Okay, picture the plant like a living. I want you to imagine you have a dashboard in your head. 5 gauges, 5 lenses. Whenever something changes at the plant, you ask 5 questions. What does this mean chemically? What happens in the tank? What happens to cost? What happens to safety? What happens to compliance? And then one final zoom out. What happens to the receiving river? This is the theory, plant, river loop. Not because you're trying to be philosophical, because this is how you avoid getting blindsided. This is how you stop being the person who reacts late. This is how you become the person who predicts the movie before it happens. All right, high BOD event. Let's run it. Loop step 1. What does this mean chemically? When we say high BOD, in plain language, we mean there is more oxygen hunger entering the plant. That's it. More food for microbes, yes, but more importantly, more demand for oxygen. BOD containing waste is like a crowd walking into a small restaurant. The restaurant only has so many chairs, only so many cooks, only so much air inside. If 20 people walk in, the room is fine. If 20,000 people walk in at once, the restaurant is stressed. There is a possibility that the restaurant does not have enough resources to feed the hunger of all 20,000 people because the load is too sudden and too high. So chemically, high BOD means more organic waste has entered, more microbes will be eating, more oxygen will be pulled out of the wastewater by these microbes. And I want you to connect this to what you've already learned earlier in this subject. We talked about invisible enemies. We talked about BOD stealing oxygen from rivers. Now we're seeing the same villain, but inside the plant first. Same villain, different scene. Loop step 2. What happens in the tank? Now we zoom inside the aeration basin. I want you to imagine you're in the tank. You're not a student, you're a tiny worker. You're a microbe. You live in this brown water city. Your job is to eat waste. And today, food is raining from the sky. At first, you're excited. You're excited to achieve your life's purpose. You happily eat, breathe in oxygen from the water, multiply to create more microbes like you. They eat, they breathe in oxygen, they create more microbes like them. It's explosive growth. The sudden rain of food has allowed you to create billions of great-grandchildren microbes in no time. But then you start to realize that with every bite your microbes take, they must also keep breathing in oxygen. But oxygen is very limited in this water, and it is starting to run out. So what happens when high BOD hits? The oxygen withdrawals speed up. Now think like an operator. If withdrawals increase, what must happen? Either you increase oxygen supply, or oxygen in the tank drops until the microbes can't breathe, and then they start to die. That's not advanced science, that's common sense. Now listen carefully, because this is where we plant a seed that will later become math, but right now it's just logic. If more BOD comes in than the microbes can eat, what happens? Pause. Say it out loud if you want. The BOD builds up. The BOD accumulates. And if the BOD builds up in the plant, where does it eventually go? It goes out of the wastewater treatment plant without being fully destroyed. It becomes effluent. This single idea is your first mass balance instinct. Not an equation, a question. Is the plant removing what's coming in fast enough? If yes, then there is stability. If no, then the waste will accumulate and drift toward trouble. You don't need to see letters and formulas to understand this. You need to feel it as a story. A bathtub with a drain. If the faucet is faster than the drain, the tub rises. Same logic, different place. And now you can sense the chain reaction beginning. High BOD, oxygen demand rises, dissolved oxygen in the water can drop, microbes can start to die, treatment can weaken, and effluent can worsen. No panic, just cause and effect. Loop step 3. What happens to cost? Now the camera leaves the tank. We walk into the blower room. This is the room where the blowers supply bubbled air to the wastewater inside an aeration tank. It's loud in the blower room, and it's hot. But this is the heartbeat of the plant. Here's the rule. When oxygen demand rises, air equipment works harder to supply air bubbles to the aeration tank. Harder work equals requires more electricity. More electricity equals requires more money. So a high BOD day can cost the plant in ways people outside never see. And it's not just power. If the plant responds by adding chemical support, that's cost. If the plant produces more sludge that must be handled, that's cost too. If the plant becomes unstable and needs overtime labor, that's cost too. This is why operators who understand the loop become valuable. They don't just keep water clean, they protect budgets. And exam writers love this kind of thinking. They ask questions like, which operational change increases energy use? What condition leads to higher aeration demand? If you can run the loop, you don't guess, you reason. Loop step 4. What happens to safety? Now we turn to the one topic plants can never afford to ignore: safety. Here's how I want you to think. Safety is not a separate checklist floating in the air. Safety is what happens when chemistry and equipment meet reality. If oxygen suddenly drops and the microbes start to die, odor can rise. Odor isn't just unpleasant, it can be a warning sign. If processes get stressed, foam can show up. Foam can hide walkways and edges and create slips. If operators rush to make sudden adjustments under pressure, mistakes can happen. And in a plant, small mistakes can become big consequences. So you learn this mental habit. When the process gets stressed, the job gets riskier. This is why predicting the movie early is safety. Loop step 5. What happens to compliance? Now we enter the world of the permit, the guardrail. Remember the earlier lesson? Compliance is not hitting the guardrail. So the question becomes simple. If BOD removal weakens, what happens? Effluent BOD rises. If effluent rises, what happens? You move closer to the regulatory limit that has been set for BOD level in effluent wastewater. And if another stress hits, rain, flow swings, temperature changes, power outage, your safety margin shrinks even further. This is the key idea. Compliance is the final report card of every internal decision. Even if the plant feels okay, the numbers may be drifting. And exam questions are built exactly like this. They don't ask you to recite poetry. They ask, what happens to effluent if influence strength increases? What is the risk if DO cannot keep up with incoming BOD waste? Which change could push the plant toward a violation? This loop gives you a map. Now let's zoom out. We leave the plant fence line, we follow the outfall pipe, we enter the river. And we remember the downstream neighbor story. If effluent BOD rises, the river's oxygen gets pulled down. Fish don't read reports. They only feel the oxygen decline. Kids skipping stones don't see lab sheets. They see the floating fish. They see the dead zones. The downstream neighbor doesn't know what BOD stands for. They just know something feels wrong with our river. That's the final purpose of the loop. Theory to plant to river. This is not classroom thinking. This is responsibility thinking. Now imagine you're sitting in an exam. You see a question. Influent BOD suddenly increases. What is most likely to happen? The best way is to run the loop in your mind. Chemically, there is more oxygen hunger. Tank, dissolved oxygen goes down, treatment tank gets stressed. Cost, demand for air supply or aeration goes up. Safety, there is higher risk of system getting upset, risk of odors, foam, rushed decisions. Compliance, effluent BOD could rise. The BOD levels get closer to regulatory limits. The margin shrinks. River, oxygen stress is added downstream. Great! You just answered 5 questions without memorizing 5 facts. In summary, you are not just adjusting a blower. As an operator, you are managing oxygen debt. And here is a sentence you can carry for life. If more goes in than comes out, something builds up. And when something builds up, somebody must pay. This loop is your compass. Now, here's the question that leads us into the next lesson. What decisions can I make to prevent system failure?